Greetings. My name is Dan Boudreau, and I'm the Geospatial Systems Lead with GZA Geoenvironmental. This presentation highlights a 360-degree use of the ArcGIS Platform to support geodesign for coastal resilience planning, design, construction, and observation and adaptation. Today, we focus on a coastal resilience study for the town of Old Saybrook, Connecticut, which is located along the coast on Long Island Sound. This particular study was funded by a block grant from the U.S. Department of Housing and Urban Development, otherwise known as HUD. Many grant funding opportunities like this one emerged as a result of the effects of Hurricane Sandy, which occurred in the days between October 22nd and November 2nd in 2012. Superstorm Sandy, as it came to be known, was one of the deadliest and most destructive, as well as the strongest hurricane of that particular season, inflicting nearly $70 billion in damage and killing 233 people in the process across 8 countries, from the Caribbean all the way up to Canada. Resilience studies like this are used by municipalities to make decisions in terms of capital budgeting, accessing other grant opportunities, dealing with regulations, and planning to create future resilience. In this case, resilience is in terms of the risk of coastal flooding, which is getting worse as a result of climate change and sea level rise. In the state of Connecticut, all of these plans at the municipal level are consolidated to form an overall statewide approach and resilience plan. GZA's approach to conducting these studies is to employ state-of-the-science practices along with probability to examine risk. This framework is referred to as risk-informed decision-making, which is a probabilistic approach to making decisions. High-resolution hydrodynamic flood modeling is used to supplement flood hazard analysis performed by FEMA and the U.S. Army Corps of Engineers. A key aspect of this process is, of course, the ArcGIS Platform, which includes the capabilities of desktop, web, and mobile GIS, and serves many roles, including a system of record, data integration platform providing design support, and a system of engagement for the project team and stakeholders. All of this is combined to develop resilience and adaptation strategies, along with actions and measures consistent with the community's vision and plans for development. The backbone for these studies is a framework built around the ArcGIS Platform, including ArcGIS Enterprise. It begins with the data tier, which includes site-specific information, such as topography, planimetrics, hard assets like structures and other infrastructure like stormwater systems and roadways. Other information, such as demographic data and assessors information, is also included. Various applications at the modeling tier are employed to characterize flooding, as well as vulnerability, estimate losses, and also process model outputs for integration with the geodatabases. All this information is published as services and displayed in a series of maps. This information is also augmented by a number of authoritative services hosted by local, state, and federal sources, which feed into models, as well as geoprocessing tools, and are also displayed in web maps. Many of these authoritative services have been cataloged as map and feature service items in our portal for easy discovery and use. In addition, we host and maintain a number of map service and feature services that support internal organizational workflows for various technical practices. At the application tier, custom web applications provide primary visualization, screening, and custom printing capabilities through a series of services and custom widgets. Additionally, the inventory and evaluation of infrastructure and assets is augmented with mobile GIS through applications like Collector and Survey 123. Strategies and potential measures are moved into conceptual design in CAD, with data being shared directly between AutoCAD and ArcGIS through connections or export, translate, and load, otherwise known as ETL processes. Alternative design scenarios are tested at the modeling tier, with results shared all the way up to the application tier and ultimately moved to final design and later construction. The study methodology is based on a discrete 5-step process. First, we begin with an inventory and cataloging of the physical site characteristics along with specific town assets. This is followed by the characterization of flood hazards, which is largely based on numerical modeling to characterize flooding, employing applications like AdCirc, SWAN, and others. The modeling results are processed using Python to develop raster layers and vector feature classes in a geodatabase, which are then published as the map and image services for access in our GeoTool web mapping application developed using Web App Builder for ArcGIS. Next, assets are stressed relative to the flood hazards to determine their vulnerability. Resilience and adaptation strategies are identified and developed along with actions and measures which are shared with the public in a collaborative, iterative, and participatory process comprised of workshops. These workshops are often facilitated by WebGIS. Finally, this process culminates in identifying specific actions and measures along with steps for implementation. Once adopted by the community, the study becomes a blueprint for implementing resilience going forward. For this project, the asset and infrastructure inventory included well over 500 discrete layers of information stored in the project geodatabase, which has been designed with a schema to support resilience studies and integrate with other applications such as FEMA's HAZUS-MH, AutoCAD, and the modeling apps we've displayed already. Some of the asset layers are displayed here in our Natural Hazard Risk Management web mapping application. This application is a custom targeted deployment of Web App Builder designed to support the Natural Hazards Planning and Resilience team at GZA. It combines thousands of pre-selected and categorized map service and feature layers, some of which are hosted by us. It includes custom widgets and links to numerous internally managed and external authoritative resources, such as document templates, custom Excel workbooks, and other analytical apps, along with guidance documents and other external web resources. GeoTools like this one are employed by GZA's engineers, scientists, and project managers in tandem with desktop and mobile GIS and other applications to support our workflows and project execution. From there, the characterization of coastal flooding examines FEMA coastal flood hazards and the 100-year recurrence interval. This is combined with sea level rise projections and moves into higher probability flooding events. These flooding events are modeled for multiple recurrence times, or what's called return periods, and account for different sea level rise projections. For this project, over 60 different coastal flood scenarios were modeled, employing numerical flood simulations, including storm surge and bathtub modeling based on total water levels. The modeling also included waves depicting height and direction. All the inundation and wave modeling outputs were processed employing the custom geoprocessing toolbox to convert them from ASCII irregular point grids to raster and vector layers in the geodatabase. These were published as services to be viewed in web, desktop, mobile GIS, and for figures in document production. Flood hazard risk was characterized for several discrete categories of assets, such as essential facilities like police and fire for emergency response, lifeline facilities for potable water and power systems, and high potential loss facilities like dams, where their failure could result in a significant loss of life. Various geographic areas, such as neighborhoods and commercial districts, were also examined. Operational and functional systems are also included, such as those supporting emergency response, as well as the stormwater system's ability to convey water during a significant flooding event, and the ability of transportation networks to remain functional. Key natural resources, such as marshes, beaches, and dunes, were also stressed to quantify the risk to them under the flood scenarios and undermine their ability to mitigate flooding. The roadway network was examined with risk and impacts quantified for each flood scenario as shown here. Employing high-resolution LiDAR terrain, the roadway elevations were derived to quantify flooding depths. These results were summarized and output as formatted tables for direct inclusion in the report. Employing FEMA's HAZUS-MH, Economic risk was analyzed at multiple levels of resolution, including census block, parcels and properties, and discrete structures to calculate economic losses and compare those results with claim requirements to the National Flood Insurance Program. The results from HAZIS were exported to the Project GeoDatabase and published as a map service. I'd like to point out that all the layers in the GeoDatabase and services were directly used to generate the report figures you've seen here. Custom print services provide various pre-formatted output sizes, allowing staff to generate figures and image vignettes to include directly in the report in a self-service fashion. Potential adaptation strategies, actions, and measures were evaluated and shared with the public through a series of workshops. These collaborative sessions included tabletop exercises. The use of large printed maps were augmented with the interactive use of the GeoTool web mapping application, which was projected on a large screen to allow access to key project data interactively. This resulted in recommendations and adaptation alternatives outlined in the report, such as guidelines for future development. A key component of the analysis included shoreline change. Historical data and information compiled by the University of Connecticut's Sea Grant Shoreline Change Project were included on this project and served to support developing adaptation strategies and mitigation measures. One such opportunity emerged at the beach, adjacent to the former home of Katharine Hepburn as part of the Hepburn Preserve. This led to the development of a measure employing a living shoreline approach to mitigate the adverse effects of wave action, particularly during significant coastal storms. Various conceptual designs were developed in CAD from data coming directly from the Project GeoDatabase. Alternative scenarios were then model tested. Here's a comparison of wave action in both direction and height. Existing conditions showing prevailing wave action are displayed on the top. On the bottom, the resulting mitigating effects on waves were depicted with the proposed measures in place. This was resulted from augmenting the LiDAR data to reflect those structures on the surface. Dune erosion resulting from wave action employing the proposed measure was modeled under multiple return periods, including 10-year as well as 100-year probabilistic conditions. Each of the scenario results were pushed to the Project GeoDatabase to provide visualization via the GeoTool web mapping application and stored along with the modeling parameters for future use. Local ecological characterization of the shoreline and the adjacent marsh area was conducted using data gathered in the field with Collector for ArcGIS. This included hundreds of photographs and features mapped using that software. Proposed measures included restoration of the local marsh vegetation to mitigate the effects of the dune erosion. The Living Shoreline moved through a series of conceptual design options developed in CAD and were scenario tested using the modeling. This slide depicts the chosen option employing stone sills along with construction of a new marsh and dune with native plantings. The rendered view is in the upper right to show what this will look like after construction. Ultimately, this option did move to final design and construction began this past fall. Thank you for your time today. And if you wish to reach out to me after this presentation with any questions or want to discuss ArcGIS or coastal resiliency in general, you can please reach out to me at my email address shown below, daniel.boudreau@gza.com. Thank you.